All right, good evening, everyone. Can everyone hear me okay? So where's my chat? All right, perfect. Okay, so a few things before we get started. We'll look at, so there is a site, where is it? Some of you might be interested in. It is a, there's some videos on how to be successful at online classes. And so it's posted on Discord and See You Learn, but I'll post it here as well. I didn't watch it, but one of the TA coordinators watched it and said it was particularly relevant. So there you go. It's another resource for you. All right, I will. Let's look at the calendar first, and then we will look at. Well, we can decide from there what we're going to do, but. Okay, so here's the calendar. I started the recording. Oh yeah, and there's a, yeah. All right, so we are here, and so there is a quiz that's been released, and that quiz is from, so it started last night, and it's good until Wednesday at midnight. So make sure that you do it within that time. And we'll look over the, we can go over the practice quiz if you like, if there's any questions on that. And the assignment you should have submitted on Saturday. And there are solutions that have been posted. So if you have any questions on those solutions, feel free to ask and we'll go over it. They seem to be pretty straightforward, but I can definitely answer questions. Question 2 of the practice quiz is kind of tricky. Okay, yeah, we can take a look at that. So yeah, now we're back into the busy time. So assignment 2 has actually been posted as well. And so that's due on June 20th. So that's roughly 3 weeks from now. And I should have a copy of it open so we can look at that too. But first, let's look at the practice quiz. Oh yes, so I've reminded myself multiple times to start recording. So somebody did ask about question 2. I think this one should be pretty straightforward. You should know how to do a truth table. It's one of the easier things, but it, you know, be very mindful of the brackets, that you do things in the proper order. Right, so this one you have to, essentially what you want to do is you want to take this expression and use logical equivalences and transform it into either a true value, a false value, or you want to put it in disjunctive normal form, full disjunctive normal form to prove that it's a contingency. So the one on the quiz that you will be doing is much, much simpler. This is more difficult because it's practice. So if you could do this, you should be fine on the quiz. To be honest, I don't even know the answer to this. I didn't have the solutions, but we can work through it if you like, or attempt to. If that's, do you guys want to work through this problem? Okay. Well, let's give it a shot then. So, like I said, I haven't done this previously, but so the first thing I would do is I would apply. Yeah, I would probably apply the De Morgans here. So I would start with not Q or not R, and then that's or. Sorry, that would be and, not R. P or Q, and not P or R. Okay, so that, and that is De Morgan's law. And we should, of course, be numbering these lines as well. All right, so now we have conjunction, disjunction. Yeah, this is a little bit tricky, eh? So I would do, so I would take this guy here, and you can distribute it inside this expression. All right, so what do I mean by that? Well, let's see here. So I'll write out the parts that I'm not going to manipulate first. And then, so P or Q, and wait, no, I don't want to do that. Yeah, that's a good question. P or Q and not P. Or P or Q and R. You know what? I was completely unprepared for this. So when we take the break, I'll go through it, I'll find the solution, and then we'll work through it, rather than me sitting here humming and hawing for 10 minutes. So we'll come back to this one after the break, okay? Yeah, that is trickier than I thought. Any questions on this question 3? So this is basically almost exactly what you're going to see on the quiz, except of course it'll be a little bit different. And we'll have 2 marks for simply identifying the logical equivalence to this phrase, and then another mark for finding something that's logically equivalent. All right. So all eagles have feathers. Is this the 3rd question? Is this the one you mean, Nathan? All right. So all eagles have feathers. So which one is the first one? The translated predicate logic expression, the one that directly refers to this statement. A, yeah. So this one says for everything, for all animals, if it is an eagle, then it has feathers, and that translates roughly to all eagles have feathers. Okay, so then what would the logically equivalent thing be? Well, there's 2 things we're dealing with here. We're dealing with predicate logic, and we're also dealing with, of course, regular logical expressions. Yeah, B is the equivalent one. So, but let's work through it a little bit. So first of all, we would say we could look at all the for alls. So there's only 2 of them, and we can clearly see that this expression is not equivalent to this one. This one is actually so you could use implication equivalence to simplify this, which is what we did. So if you did implication equivalence, we could say for all x, not e of x or f of x, and then we can do reverse De Morgan's. So this is, I'll put down the rules, but you don't, of course, on the quiz, it is multiple choice, so we won't have to. And then I could do De Morgan's on that. So for all x, not, and then I have not e of x here and not f of x. And that's De Morgan's. Then I could simplify it a bit. So I could take out this double negation. So double negation. And then, so here I'm basically doing the reverse operation of, if I started with this guy, I can easily take the negation of that by flipping the there exists to a for all, and then applying the negation here. So if I do that operation in reverse, then I end up at this there exists an x such that e of x and f of x. And that is the, what do we call that? That's the, I don't even remember the name, but that's just the quantifier equivalence, whatever that. I don't remember the name off the top of my head. Okay. So is that sort of clear? And this one, more so than the rest, is almost identical to what you're going to see on the oops, sorry. Okay, any questions on number 3 then? All right, number 4, this should be very straightforward. So you could simply do, since it is a quiz, you can just do as much shorthand as you like, but we could say if 20 is greater than 21, or 14 is greater than 12, then, and say 12 is less than 15, well, that's, we know is true. Or 14 is less than 11. So we can simplify that more. If false or true, then true or false. And we want to keep, so I didn't put the brackets in here, but, and in fact, this is a little bit ambiguous. So I think I put the brackets in on the quiz, but if I didn't, you know, make a note of it. So implicitly, the brackets, these I don't need brackets for because it occurs within that if-then statement. But here, I could have implicitly had brackets here. So then this is logically a statement too, but it's going to have a different different meaning and possibly a different answer. So I'll have to go back and check that. If that happens to be the case where I didn't explicitly put the brackets and it is a different answer, then everybody will get the mark for that. But yeah, but you should, you know, the brackets might be, I might have put the brackets here, but not here, but I don't need them here because there's no other way to parse that. That's the only way. So then this is basically true implies true, and which is equal to true. Okay. Any questions on that one? Those you should be able to do fairly quickly as long as you remember your implication truth table and stuff like that. Number 5, state the inverse, converse, and contrapositive of the following implication expression as English sentences. Ensure that you list the symbols. So I did the symbols in advance. And this is basically if E, then not I, and not D. So now I want, if I want the inverse of that, then I would say, or I could write it as an implication. Let's simplify it. So that is equivalent to this. To take the inverse is to swap them. Inverse, converse. Man, am I forgetting this? Yeah, so the inverse is not. So then I would say, if it is not impossible and it is not difficult, then it is entertaining. Converse, I would say, not E, so this is inverse. implies, and then I would want to simplify this before I translated it. So I would apply De Morgan's to this expression here, and I would get I or D. So then I would say if it's not entertaining, then it is impossible or it is difficult. And the contrapositive is then not E, and then I would simplify this again to using De Morgan's to I or D. So then the contrapositive expression is that if it is impossible or it is difficult, then it is not entertaining. Okay. So again, this is more complicated than what you're going to see on the quiz. On the quiz, these are multiple choice, but I did 2 of them, and you have to identify either the inverse, the converse, or the contrapositive of each of them. So it's slightly less work than you have here, but around the same ideas. So you would convert them and then look at the expression you got and translate it back in English and see that it matches one of the ones listed. Okay. So any questions on number 5 then? Or do I still have my video on? Okay. The model solutions for the assignment, the quiz. I think that's it. Is there any questions on any other material? So if not, we'll start the lecture. It's going to be a little bit different this time in that I'm using OneNote because the examples are getting larger and more complicated, and they're a lot harder to work out on the limited space of a PowerPoint presentation. Grades for tutorial 1 are up. No, but thanks for the reminder. I'll write that down. So I'll release the grades for tutorial 1. Yeah, the answers for assignment 1 are posted. They're on CU Learn. I guess I will actually, I'll write down a reminder too. I'll post them on Discord. Okay. All right. And then I was going to, somebody wanted to see the answer for question 3 on the practice quiz. Do you still need to see the answer for that? Yeah, I believe that was just a second ago, eh? So I'll show you that. So question 3, so the answers are A and B. So A is the first one and B is the second one. So A would be worth 2 marks, and it's a direct translation of this, and B would be worth 1 mark, and it's not a direct translation, but it's logically equivalent. And generally speaking, it might be the, you know, you take the quantifier and negate it, and that is probably what it is, although not guaranteed. So yeah, that's and to do that, we took A, and then we did a bunch of just basically inference rules and logically equivalent statements to get down to this one, which was B. Okay, so is that okay, or is there any questions on question 3? Okie dokie. All right. Okay, let's go to OneNote. Why C is not correct? Sure. Let me see here. Yeah, because in C, what I'm saying is that so the universe of discourse is all animals, and so C is saying basically that all animals are eagles and have feathers. So it's in a sense too strong. Yeah, not all animals are eagles, exactly. So it's correct in the sense that it says that all eagles have feathers, but it also says that everything is an eagle, which is more than we wanted to say. All right. So yeah, it is sort of tricky in that sense because it does say what you want to say, but it says too much. All right. So good. Any questions on that? All right. Okay, and so today, I don't know how much of this material we'll get through. Like I said, this is going to be a little bit different than the normal lectures because I'll be writing a lot more and we'll be going through more examples in more detail because we're putting together a lot of the ideas that we've seen so far into doing proofs, and that gets, you know, there's some important details that we should be working through and not skipping over. So, you know, PowerPoint slides are very good for high level presentations, but when you start to get down to the details, they're kind of constrictive. So we're going to give this a try. So last week we talked about the introduction to predicate logic was the first topic. So that's the for all, and there exists the quantifiers, and we talked about how we bind variables with quantifiers, and then what those things mean and how we translate them to and from English. And then we started in on inference and argument. So we looked at what is an argument, what's a valid argument, what's a sound argument. We looked at what a deduction is, some of the rules of inference, and then what a proof is. And basically, these are all, basically an argument is an implication and a proof is a very, like a complicated implication. So in a sense, these are not too different arguments, deductions, and proofs. It's just the deduction and the proof can be more complicated. They can have more steps. So yeah. So this week, we're going to combine those two ideas. We're going to talk about arguing with quantified predicates. So we said before that we can't really argue. We can't use these rules of inference with quantified predicates, which is true, but we can convert them into some form that we can then use and argue with, and then convert them back into a quantified predicate if we want. So we're going to talk about how to go from quantified predicates to logical inference and back again. So once we're in the logical inference, then we can use our regular arguments and get to the conclusion that we want, and then we can transform back into a quantified predicate if we want. And then after that, we're going to start looking at formal proof methods. So in a sense, you know how to do proofs, but this is going to give you more tools for your toolbox. Sometimes straightforward proofs don't work that well, so we have other strategies that we use. So we're going to look at different approaches to proofs, and we're going to look at we're going to look at different types of proofs. And then, depending on how quickly we get through it, we'll look at introduction to induction. So this is a type of proof. And it's a highly generalizable way to argue for all. So this quantified predicate idea, where we say something is true for all of these things, induction is one way to argue that. We're going to look at some of the different applications of it, and then we'll look at weak and strong induction. And so your second assignment has 2 questions on induction, one on weak induction and one on strong induction. So at least 2. Maybe more. Okay. So the first topic, arguing with quantified predicates. So we talked about before how the rules of inference do not apply to quantified statements. So we can, in a sense, we saw earlier on the quiz where we did 4x, blah, 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 blah. And then you can apply the inference rules inside the brackets here, but you couldn't really argue anything outside the brackets. So to perform inference with predicate logic, the quantifiers must be removed and then later restored. So yeah, so as long as we have this quantifier out here, then these, although we can do operations inside the brackets, they're sort of trapped there. We can't combine them with other logical expressions, which is what we want. So we want to be able to take those and combine them with other logical expressions and then argue from there. And then we'll later restore them if we want. So one way to go from a quantifier to a regular logical argument is called universal instantiation. So if we take a statement for all x, p of x, what we can do is we can choose an item c and conclude that, well, if c is part of the universe of discourse, so then of course p of x must be true for this element c as well. And now c is a specific element that we can work with, and we'll see examples of how to work with it. But for now, you know, this should be clear. So if p of x is true for all elements x that are in the universe of discourse, then it must be true for any specific element c, right? And so one example is if the universe is all mammals and w of x represents that x is warm-blooded, then for all x, w of x means every mammal is warm-blooded. And then thus any specific example of a mammal must also be warm-blooded, right? So an example of that is, if you give me the statement, or if I state that, and it's true that for all x, w of x, all animals are warm-blooded, then I can choose any animal, say a kangaroo, and conclude that the kangaroo is also warm-blooded. Okay? So does that make sense? Yeah, all right. So I'm not going to go full screen because I can't see the chat when I do that. All right. So does this make sense? Any questions on this? And I could say, you know, for all mammals, so, you know, a whale is warm-blooded, for instance, or whatever. I can choose any mammal and it must be warm-blooded. So we have existential generalization. So given P of C, so I have some claim that I'm making about a specific thing, I can conclude there exists an X such that P of X is true. Right? So if there is if I have an example of something for which a predicate is true, then I can conclude that, well, there must exist an example of this being true. Right? And this is repeating what I said. If P of C is true for a specific element C, then there exists at least one element X for which P of X is true. So again, if the universe is all mammals and WX means X is warm-blooded, and I say, I can say, if I say W tiger, then tigers are warm-blooded. And since a tiger is a mammal, at least one mammal is warm-blooded. So then I can claim, given some specific example of a warm-blooded mammal, I could conclude there exists an X such that exists a mammal such that that mammal is warm-blooded. All right. Good, clear, questions? Okay. Universal generalization. So for an arbitrary element C, I can claim P of C. So now, what do we mean by arbitrary element? So if I say arbitrary, that means it could be any element in the universe. So I've chosen an element, but I've said nothing specific about it. I've just said I could take basically anything from the universe and conclude P of C. And so based on that, I can conclude for all x, P of x, right? So the important part of that is that it's an arbitrary element, C. So I know nothing else about it. All right, so if I know P of C is true for an arbitrary element, it follows that P of x must be true for any and every element x in the universe. And you can think of it as I select at random. And if I select at random and something is true of that thing, then it must be true of all things. But it's not real. This might be a little misleading. Arbitrary is a better word, but I'm just trying to grease the wheels a little bit. So if I can choose any mammal Y and say that Y is warm-blooded, then all mammals must be warm-blooded. Okay, good questions. Existential instantiation. So for an arbitrary element C, if I say there exists an x such that P of x is true, then I can conclude that I can take that example and conclude that for this specific example, P of C is true. So we can select that example of the element, but note, we know nothing else about it. So there's no other facts about it other than whatever this predicate is. So element C, it's not arbitrary in this case. It is chosen specifically for having the property P. For example, if there's at least one mammal X such that it is warm-blooded, then it follows that I can select that mammal and assign it to a variable Y, and then we would say that Y is a warm-blooded mammal. Because I know that one exists, so I can select that one, let's say, or at least one exists. Okay, good. Any questions? Hopefully this is clear. So let's look at a sample argument then, how we would put these things into operation. So, let's say I have this premise here that X is a man, and let O of X be that X is mortal. So then I could say, one of my premises in my argument is that all men are mortal. So then what I would write here is, for all X, what should I write? So I want to state that all men are mortal. So M of X, and again, we just sort of, we did sort of look at that on the quiz. When we want to make statements like that, so here they, actually I didn't even define the universe of discourse, but you could say that the universe of discourse is all entities. So then here's our argument for all men is mortal. All men are mortal. Socrates is a man. Well, that's easy enough. I can say that S is for Socrates. And then this statement means that Socrates is a man based on my definition up here. And then I want to prove Socrates is mortal. So I want to prove that O of S. So this is the argument I'm trying to make. These are the facts that I'm dealing with. But of course, I have this quantified predicate here. So to prove O of S, I would have my two facts here, the one with the quantified predicate, and then the fact that Socrates is a man. And then I would do So I could take number 1. So since Socrates is a man, and Socrates is an entity, and for all entities, if it is a man, then it is mortal, then I can use universal instantiation along with 1. All right, so I can choose Socrates out of my universe of discourse, and since he is a man, I can apply this argument. Or, well, even if he's not a man, I could still apply that argument, but specifically because he is a man, this would work in this case. And then I can just do, sorry, this is, so 2 and 3, modus ponens. And that's it. So I've successfully argued by stripping away my universal quantifier in a sense. And then once I did that, then I can make the regular arguments that we've seen last week. Okay. So any questions on that? P of C, it means that there is a variable passed through X. In a sense, P of C, so I can put any argument into the into my predicate here. So I generally, X is sort of, or N might be reserved for generic, or C might be something specific, but that's just a convention. We can put anything we want in here. All I'm saying is that whatever entity is contained in my variable Y, or, you know, if I use something explicit like tiger, then I'd say that this predicate is true for that item. So I'm not really passing it through X. X we just use sometimes to mean something generic. So we often use it with these with the quantifiers basically, because we want to stay away from being too specific at that point. So hopefully that answers your question. Yeah, some of these concepts at this point, the concepts are starting to pile on each other, and so it might get a little bit complicated. So just try and hang in there, ask questions, and we can go over anything you like. All right, so let's look at another sample argument. So we have a predicate S of X, meaning X is a student, C of X, X has taken this class before, and L of X, X will learn some discrete math. Again, I haven't been specific about the universe of discourse, so you can, in a sense, assume is all entities. So that does work as long as, you know, we're defining our entities using this predicate. So the things that we're going to operate on they're either students, or they are somebody who's taken this class before, or something that's taken this class before, or something that's learned some discrete math. So logically, it still works if we take the broadest possible universe of discourse in this case. All right, so let's look at our argument then. The premise is some students have not taken the course before. Everyone in this course will learn some discrete math, and we want to prove that someone who learns some discrete math will not have taken this course before. So let's shrink that a little bit. All right, so some students some students have not taken the course before. So so we want to build our expression here. So which quantifier is that? Some students. Yeah, well, yeah, S of X. I mean, so when I say quantifier, I mean existence, correct. Yeah, so when I say quantifier, what I mean is that either there exists or for all. So I'd say there exists And then yes, I would say S of X. So you were correct in that respect. And then what is it? Do you guys remember? Is it implication or conjunction here? So we want, so not have taken the course, we want this C of X, but we need some way to connect them. Conjunction, yeah, correct. So if I use the implication, that would be too weak, because I'm saying there exists something, and if it is this thing, if it is a student, then they have not taken the course before. And well, my thing that there exists X might not be a student in that case. But here I'm explicitly saying that there exists an X that is a student and has not taken the course before. Everyone in this course will learn some discrete math. So which quantifier is that? Yeah, for all. So everyone in this course, so that's our C of X. And then we'll learn some discrete math. So we're going to say L of X. And then we just need to connect them. So either with conjunction or with an implication. So which one is there? Implication, yeah, correct. Right, so if we use conjunction, then it's too strong. We're saying that everything that exists has taken this course before and learned some discrete math. So yeah, here's the correct expression. And then what we want to prove is that someone who learns discrete math will not have taken the course before. So which quantifier again? Someone? Yeah, exists. Yeah, 3x. Yes. Yeah. So there exists. If I say someone, then I'm being sort of. There exists an x such that, and again, so we've learned some discrete math and will not have taken the course before. And generally speaking, although this is not a hard and fast rule, but when you use there exists, you want to use the conjunction. And generally speaking, if you use the for all, it's the implication. It's not always true, but in a lot of cases it is true. So don't take that as gospel, but do try it out first and see if it works. So good. So we have our two premises. This forms our knowledge base. And we want to prove, now we want to prove something with a quantified predicate again. So now we want to use, so when we want to go from a quantified predicate to just a proposition, we use instantiation. And when we want to go back from something specific to something general, we use generalization. And if I confuse them, just speak up. So in this case, we want to use instantiation because we can't argue with these. So we want to instantiate them, but which order should we instantiate them in? Or does it matter? Should we do 1 first or 2 first? Yeah, 1 first. And we'll see why. So I'm saying there exists an x such that that x is a student and it didn't take the course before. So I'm going to instantiate our y. Instantiation in programming. I guess it would be, I guess, but it's only in the vaguest sense. I would have to think about that a little bit. Yeah, so when you instantiate something, yeah, I guess it sort of is, yeah. Although it's not quite exact, but it's similar. So you instantiate a variable or something. So then you're bringing it into an existence with a specific value, and that's sort of what we're doing here. So yeah, it does apply in that sense. It's not a perfect analogy, but it's not a bad one. Okay, so now we have this guy, and then we want to use. So this is existential instantiation. So I'm going to do a short form here. And then we use, so now we want to argue with this, this y. And that's why we do the there exists first, because, well, now I can say s of y, sorry, that should be a y, not an x. So that means that y is a student who has learned some discrete math. And this is universal instantiation. Okay, so now we have our argument in predicate in propositional logic form. So what would happen if we had done it the other way? So let's take a look at. So let's say if we did this again and we said s of y implies L of y. So I did my universal instantiation first, and then I wanted to do s of y and not c of y by existential generalization or instantiation. But why is that a problem? Does anybody have an idea? So why can't we do that? It's because we can't. That's not logically consistent. Right? So we've chosen, when we choose something for all and we do this universal instantiation, right, we don't know which one we've chosen. So we've chosen one arbitrary item, but we don't know if it's this specific item. So we're saying there exists something that has this property. But when we choose this guy here, we don't know if we've necessarily chosen the proper one to be able to claim that. So we have to do, in general, if we want to keep our argument consistent, we have to do this existential instantiation first. Why does he order it? So let's think of an example. Yeah, okay, so let's say I'm talking about you as students, and let's say that I'm saying there exists a student and that student has not taken this course before. So I claim number one, and the student's name is Bob. All right, so now when I do this universal instantiation here, I'm saying for all students, this is true, and I'm doing universal instantiation, but I don't know that I got Bob here. I could have gotten Alice. So when I do universal instantiation, I don't know anything about, I don't know any other properties of this thing that I've instantiated. All I know is that I've picked something for which this holds true. So does that sort of make sense? Whereas if I do it the other way, I've definitely picked Bob here, and then I've said, well, since this is true for everyone, then it is also true for Bob. Okay? But if I do it the other way, then yeah, I don't want to. Yes, yes. So when I instantiate things, I'm picking a specific example out of them. And if I do the universal before the existential, then I'm not arguing logically anymore because, like I said, I could have picked Alice out of here. You don't know who you picked. Right. Good. Yeah, good questions, though. Good. Any other questions on that? All right. So from here we can finish the argument. So now we have these things that we're arguing about. Let's say y is equal to Bob. That's fine. So we can do simplification of 3 and get Bob is a student, for instance. And then I could say, and now I can look at 4 here and say, well, since this is true, I can use modus ponens to claim that this is true. So that's 4, 5, and modus ponens. And if I move through these arguments too quickly, by all means, let me know. And then, so I want this, and I have L of y, and now I kind of want this not C of x. So I can do simplification, so not C of y. And now I know that both of these things are true, so then I can use conjunction on them. So that's 6, 7 conjunction. And then 9. So now I have sort of the form that I want. I have the, the logical expression here that I want. So what's the, how do I get this existential thing here? Let's see if we followed closely enough. If not, that's completely okay. But so now I want to use a generalization step, right? So now that I know that this is true for at least one item, it's true for Bob in this case, or Y, then I could say, well, there exists an X such that is not taking the course, but will learn some discrete math. Right, so that's 8, an existential generalization. Okay, is that clear, that last step? So we basically, and so we've arrived at the conclusion we wanted, and we've proven it using, going from instantiation, so our quantifier instantiation, and then going back to a quantifier generalization after. All right, and so to review, these are the 4 rules that we use. Universal instantiation. So if we say for all x, p of x, and choose an element c, then we can state, well, p is true for c as well. Existential generalization, if we have an element for which p is true, then we can state there exists an x such that p of x. Universal generalization, if p of c is true for an arbitrary element c. So that's important, and you'll have to probably pick that up from the context. But if it's an arbitrary element, then we can state for all x, p of x. Existential instantiation, if there exists an x such that p of x, then we can select a c such that c has that property, but we don't know anything else about c. Okay. So that's arguing using quantifiers. And I think, so using quantified predicates. So 6:30, I think before we go into the next part, we will take our 10-minute break. I will work through that problem on the practice quiz. So at 6:40, we'll come back, we'll work through that, and then we'll start the next topic. So yeah, break time. All right. So let's get back to the lecture. Wrong one. Okay, so that was arguing with quantified predicates, and now we're going to talk about formal proof methods. So just a little bit of review about argument and deduction. So an argument is basically an implication of this form where we have a bunch of premises, and we know if it's a sound and valid argument, then this evaluates to true if it's valid, and if it's sound, premises are true. Oops. Yeah, and I just wrote it down here. So, okay, so it's valid if the conclusion follows from the premises, and sound if all the premises are true. So a deduction is basically a sequence of arguments with intermediate conclusions. And if the deductions are sound, it forms a proof. And the rules of inference can be used to arrive at the conclusion given the premises. And so a proof is simply a valid, true implication, perhaps with some intermediate steps. However, this here is not always that easy, this implication here. And if you wanted to, we could simplify this to say that, well, we can assign all these to a variable p, and our argument basically comes down to this implication. But sometimes this implication is tricky to navigate. So sometimes starting with p and using inference to get to c can be tricky. So there's different strategies that we use sometimes to come towards your proof in a roundabout way. So the first strategy is, of course, a direct proof, and that's just the simplest one. We take an implication, P implies C, and we assume that P is true, and use P to prove C. All right, so, and that's basically, we're just using the rules of inference in a very simple manner. All right, so let's look at, we're going to look at an example here. So we're going to show that if n is an odd integer, then n squared is an odd integer. And another way to write that is for all integers, for all n, that's an element of the integers, if n is odd, then n squared is odd. So the first thing we're going to do is choose an odd element a of the integers by universal instantiation. Yeah, and then we're going to show if a is odd is true, then a squared odd is also true. Actually, what we're selecting here, sorry. So we're not selecting an odd element, we're choosing an element a, but we're assuming that a is odd, because otherwise there's not much point. So, and we'll go over why in a little more detail in a minute. But one of the things we know about odd integers. So we're going to use this fact here. So for all x elements of the natural numbers, if x is odd if and only if there exists a k such that x is equal to 2k plus 1. Right, so that sort of makes sense. So if x was equal to 5, then k would be equal to 2, and x is equal to 2 times 2 plus 1. So anytime it's odd, we have some even number here plus 1. So we can always express an odd number, an odd integer in that fashion. So we're going to use that as a fact in our knowledge base. And since we're using a direct proof, P implies C, we're going to assume that the antecedent is true. So P also becomes a fact. So this is something that is known, and A is odd is our assumption. Because if A is odd was not true, then our implication here would be true vacuously, because If we look at the truth table for P implies C, then when P is false, then it always evaluates to true. So in order for our argument to make any sort of sense, we assume that A is odd. Okay. So we know that A is odd, or we're assuming it is, so we can use this yeah. So we know there exists a K such that A equals 2K plus 1. So I'm simplifying a little bit since, well, this is basically using 1, 2, and modus ponens. Even though that's a biconditional implication, we can, in a sense, treat the implication, we can select the implication in the direction that we want. And we're going to see a little bit later why that's true, although I think we went over it before, but this basically means this implication runs both ways, so we can use modus ponens in either direction. Okay. So then we could say A equals 2K plus 1, so that's using 3 and existential instantiation. So we had a quantified predicate here, and we got rid of it just by instantiating it, since we know that this K must exist. So we select our K. And then now we want to show that, what we want to show is that A squared is odd. That's what we want to show. So we know that A squared is equal to 2K plus 1 squared, and that is simply using 4 and math. And then we can expand out this expression. So I don't mind if you do some of the math stuff in line like this. But this is equal to 4K squared plus 4K plus 1, right? So that's just simply, this is 2K plus 1, 2K plus 1, and that is equal to this. Is everyone still following? This tends to be, some people get lost in the math here, so I just want to make sure that we're all still on the same page. Yeah, don't be afraid to raise any questions. So now what we're going to do is we're going to break this down even further. We're going to say this is equal to 2K squared plus 2K plus 1. So we're going to take out 2 as a common factor from 4 here and 4 here. Right? So these two things are still equal. And then we're going to say, let K prime equal to 2K squared plus 2K. So then 6, we could say A squared is equal to 2 times 2K squared plus 2K plus 1, which is equal to 2K prime plus 1. So is that clear what we did there? Any questions? All right, so this is basically just 5 and math. And then 7. So now that we have this K prime here, so we have a specific K prime, so we can generalize it and say, or there exists a K element of the natural numbers such that A squared equals 2K plus 1. And this is using 6 and existential generalization. And then based on that, we can go back up to this expression and state that a squared is odd. And that's 7, 1, 7, and modus ponens. All right, and basically a squared is odd because it fits the definition of odd. So to keep things a little more simple for you guys, so this is the conclusion we wanted and we got there, but you don't need to use this fact up here in your arguments. So this number 1 here, you can just state, for instance, no, this is not induction. So this is just a simple direct proof. But you can state, so if I had an argument saying, or a fact saying A is odd, then you could say A equals 2k plus 1, and just use the argument 1 and definition of odd. But for the first time, I just wanted to go through all the detail. But this argument is sufficient to say that A, if I say A is odd, then I can simply move to this using the definition of odd. And similarly, if A is even, you could just say A is equal to 2k. And that's fine. So you can go there directly without using this extra step that we put here. But yeah, we've successfully argued that. All right, so let's sort of put that as an aside. Now we could say that A is odd implies that A squared is odd, since we basically argued that. So we say if A is odd, then A squared is odd because we've assumed that A is odd and we've shown that A squared is odd. And then for 10, we can go for all n. And that's using 9 and universal generalization. Since A is an arbitrary number. Okay. So that's sort of clear, or is there any questions? This tends to be where sometimes I lose some people through these, so I'm trying to take it slow, and by all means speak up if you don't understand. So this is a direct proof. And so direct proof is simply an implication. So I have a premise, and I draw a conclusion, and then the first step is I always assume that P is true. So the first step is my fact is my antecedent is my first fact that I use, and then I can argue from there. Okay, so that's direct proof. For example of an indirect proof, so we're going to show that modus ponens for 1, 7, and line 8. Yeah. So because I did sort of skip a step here. So if I said that 1.5, even though my numbering is way off here, it should be 2. So this biconditional equivalence is, I could say that for all x element of the natural numbers, x is odd implies there exists a k and the reverse of that. So I could say, or the, not the reverse, but the inverse. So that's what it should look like. So using the biconditional equivalence, I could say that, and this is 1 and biconditional equivalence. And then I can use 1.6. I can say, I can use simplification to take this implication and this implication as separate implications, right? So I can put this one on one line and all by itself, and this one on another line all by itself, and then I can use this modus ponens argument in either direction. So yeah, I skipped a couple steps, and maybe I shouldn't have, because this biconditional equivalence is sort of well known to be an equivalence, an implication in both directions. That's why we have this little symbol of the double arrow. So yeah, to do this completely, you should break down the biconditional equivalence into 2 different implications and then use them separately. I skipped that step. But you don't have to use this particular argument. It's enough for you guys to use this one. Okay, so hopefully, does that answer your question, or? Hopefully. The answer was that I skipped a step. Okay, direct proof, indirect proof. So using an indirect proof, we're going to show that for all n, if n is greater than 0, and 4 to the power n minus 1 is prime, then n is odd. So proving this directly is difficult because we need to find a way to express a prime number as an expression. So there's no real way to express a prime number as an expression. We can only kind of say what's not a prime number, and what's not a prime number is a number that's composed of, more factors than just 1 in itself. So prime number, its only factors are 1 in itself, and a non-prime number we could express as, A times B. Yeah. Yeah, sorry. No, I occasionally skip steps so that we don't get bogged down, but I probably should have explained that one better. Okay. So since this 4n minus 1, since a prime number is difficult to express, but a not prime number is sort of relatively easy to express, we're going to use an indirect proof, which means we're going to use some logically equivalent expression. And in this case, we're going to use the contrapositive. So this is an indirect proof, is that we don't use the implication directly. We use some logically equivalent expression. Where was I here? Okay, so then, yeah, so let's say that n is the predicate, n is greater than 0, p is 4n minus 1 is prime, and O is n is odd. So I really should have arguments for all these, but I could say then, so my argument, what I want to prove is this expression here. And so then I could say if n and p, then O. So if n is greater than 0 and this is a prime number, then n is odd. That's my argument. And this is, I can also write this as this expression. So then if I want to take the contrapositive of that, I take the inverse and the converse. So it's not O implies the negation of this N and P. Right. And then we can apply De Morgan's here. Not N or not P by De Morgan's law. So instead of arguing directly, we're going to argue indirectly, and then we can argue this not P, and we can express that a lot easier. So, and this is if N is not even, is not odd, sorry, it is even, then N is less than or equal to 0, or 4 to the N minus 1 is not prime. Okay. So does everybody see how I got, so this, now I'm going to argue this, and this is logically equivalent to my original argument, which is this guy up here. But it's an indirect proof because it's in a different form. Okay, so now we have this sort of disjunction here that we have to argue. However, we can assume that N is not negative, because if N was negative, so if we go back to our original expression, so if this was false, if N was less than 0, then this expression would evaluate to false, implies N is odd, and this is always true because a false antecedent is always true no matter what. So we can sort of disregard the case where N is less than or equal to 0, and we can make the assumption that N is greater than 0, because the case where N is less than or equal to 0 we don't really care about. Since it's always true, it's trivial. So what we want to prove then is, so we want to assume N is even and prove for N minus 1 is not prime. Okay, so then our first fact is N is even. And that's our assumption. So then we could say N is equal to 2K. This is our definition of even. Like I said, we don't have to go through that complicated expression. And now this is where it's going to get a little bit mathy. So if you don't quite follow the math, that's okay. So we could say that this is equal to 4 to the 2K. So we're just substituting. So we're using 2 and math. And then it's equal to 1 times 4 to the 2K plus 0 times 4 to the K minus 1. So then we could use, well, at this point we have a quadratic expression. So I'm going to kind of do a little bit of an aside here that's just strictly math. So I'm going to let x equal for some reason I deleted that. So then so we can sort of rewrite this expression as x squared plus 0x minus 1. A squared minus b squared instead of a quadratic. Yeah, I guess. I'm not sure. Does that work? I don't know exactly what you mean, so I don't know if that'll work or not. So this is the negative b plus minus difference of squares. Again, I would have to review that. I'm not sure. That was a while ago for me, I suppose. Differences. Four squared. Oh, I see. And then yeah, I mean that is basically yeah, as long as you get two factors. But how does that give you two factors? Or is that just well known to be factorable? Yeah, I'm not sure. Okay. Yeah. Well then, yes, you can use it. So that yeah, 4 to the k minus 1, 4 to the k plus 1. Yeah, excellent. Then that's much easier than what I was going to do. So yeah, so now we've shown that through difference of squares that this is 4n minus 1 is not prime. And we would say, according to the definition of prime, and step 3. So yeah, so we've proven what we wanted to prove. Yeah, excellent. No, that's great work, guys. I have to review my difference of squares apparently, but great. So yeah, so therefore we've shown through our indirect proof using our contrapositive that that this is true. All right, so therefore, blah 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 blah. If n is greater than 0. Well, that was weird. Okay. So yeah, so this is so then you would say therefore that the original proposition was true. Okay, so now that's indirect proof, a vacuous or trivial proof. Say we want to prove that P implies C, but P is false. Then of course, P implies C always evaluates to true. So that's an example of a vacuous or trivial proof. So let's see an example of that. So let P of n denote the predicate. If n is greater than 1, then, or the proposition, then n squared is greater than n to the 4th. And we want to show that this is true for P of 0. So what we're saying basically is if 0 is greater than 1, then n squared is greater than n to the 4th, right? But what we're saying is basically false implies n squared is greater than n to the 4th. False implies false, but that happens to evaluate to true because our antecedent was false. So if we remember back to the truth tables of our implication, then if the antecedent is false, then it always evaluates to true. Okay, and that's called a vacuous proof. And it may seem to be sort of useless, but you can use it to prove properties. For example, if I have what we're going to see later, graphs. So if I have a directed graph that goes from A to B and B to C, you don't really need to know what a graph is at the moment, but if this is a transitive graph, then I would say if AB is an edge and BC is an edge, then AC must be an edge. So if this is a transitive graph, then I would have an edge here. So in this case, this is a transitive graph. But let's say I have this graph. So is this a transitive graph? Yeah. No, it is actually a transitive graph. Simply because, and it's a little bit, it's not quite intuitive sometimes, but because I'm saying if AB and BC, well, I have no BC, so this is false. So then I really have this implication of false implies whatever. No, you don't need to be that familiar with graphs. So I'm just trying to, and you don't even have to understand the example. I was hoping this was simple enough generically that, yeah, graphs are a few weeks away yet. So yeah, this is just, I do a lot of graph theory, so this is an example that I like, and it actually does come up where you're trying to prove properties of things. Oh wait, I got it right here. When you're trying to prove properties of things, you can prove them vacuously sometimes, right? So this is a transitive graph, and there's other examples where you can say, well, if it's not explicitly false, then it's true in a sense, right? So, yeah. Okay, so that was vacuous. Any questions on that? I think that's. Ah, okay. Thanks. I'll get that fixed. Huh. That's weird. All right. I'll take a look at it and get it fixed. Okay. Any other questions? All right. So biconditional proof. So this is, we saw this a little bit earlier. So if we have this biconditional implication, we can construct a proof for the logically equivalent P implies Q and Q implies P, and then prove each part separately. Right. And this is where I had earlier, I had skipped this step. So prove that n is odd if and only if n squared is odd. So this means if and only if. It's a short form. So we're going to say that let on be the predicate that n is odd, and then we can show. So we want to prove this both ways. So we want to say that n is odd if and only if n squared is odd. And so this is logically equivalent to saying that O of n implies O of n squared, and O of n squared implies, or n squared is odd implies that n is odd. So this one we're going to prove using a direct proof, and then this one we'll prove using an indirect proof. But if we prove them both, we show that they're both true, then we've shown that this biconditional implication is true. Okay, so case one. If n is odd, then n squared is odd. So our first fact is n is odd. So this is our assumption. So 2n equals 2k plus 1. This is our definition of odd. And then we can work through it basically the same way that we did before. So n squared equals 2k plus 1 squared equals 4k squared plus 4k. And then we let k prime equal and this is equal to 2k squared. And I'm rushing through it because this is precisely the same argument that we used earlier. So hopefully you remember the broad points of this. So this is 2 and math. So n squared is equal to 2k prime plus 1. So we could say that n squared is odd using 3 in the definition of odd. Right, so that's the first one proven. So the other one we're going to prove, so we want to prove that if n squared is odd, that implies that n is odd. So we're going to use the contrapositive. So we're going to say that if n is even, then n squared is even. So if it's not odd, then it must be even. So in order to prove the second part of our implication, so this should be case 2, we want to prove this. So 1, n is even. This is our assumption. N is equal to 2k. That's our definition of even. And then 3n squared equals 4k squared. That's just 2 in math. We can say let k prime equal 2k squared. And then we could say that n squared is equal to 2k prime. And then we can claim that n squared is even. All right, so then we've proven, since we've proven the implication both ways, then we've shown that we've proven our original argument, which is that n is odd if and only if n squared is odd. Good. Any questions? Okay. All right, so we got a couple more examples and then contrapositive, you don't always pick it. So indirect proofs, so direct proof is always an implication. Indirect proof can be lots of things, like indirect is basically anything else. So vacuous, and the one that we're going to look at next, which is a contradiction, is also considered an indirect proof. So when we say direct proof, we just mean I'm going to take my antecedent, my the first part of my implication, and I'm going to use it to prove the consequent, the conclusion. And basically anything else I do is indirect. So proof by contradiction. So this is actually it's one of my personal favorites because applied the right way, you can actually make a very nice short proof. So we have some claim A, and we want to show that not A is false. So what we do is we take the negation of what we want to prove, and then at some point we encounter a contradiction. So we end up with a false. Two things that contradict each other and say that, well, then that proposition must have been false. All right, so we'll go through an example. So if I want to prove a regular implication by contradiction, so P implies Q, first we can use the implication equivalence. So P implies Q is the same as not P or Q. And then we assume the negation. Well, we don't need to assume it's true. We just, we're going to argue the negation and show that it's false. So we get this not P or Q, and using De Morgan's, we can get this to not P and not Q. So if we if our consequent is true and the if our antecedent is true and the consequent is false, then that's true, but we're going to show that this leads to a contradiction. All right, so hopefully this will not too confusing at this point. So let's argue this. We want to prove for a real number n, if n squared is even, then n is even. So we can go through all the same steps. So the implication, if we use the implication equivalence, we could say that not n squared is even, or n is even. Then we take the negation of that, and we get, so if we take the negation, then we get through De Morgan's, we get this is even and n is not even. And so if we simplify that even further, we get n squared is even and n is odd. All right, so we're assuming the opposite. So we're taking the negation of the thing we want to prove, and we're going to show that that comes out to be false. All right, so then as our facts, so this would be our first fact. This is our assumption. 2, we could say n is odd. That's using 1 and simplification. N equals 2k plus 1. That's 2, and using the definition of odd. And then 4n squared equals 2k plus 1 squared. So this is, we've done this twice now, so this is the third time. So it's 4k squared plus 4k plus 1. We let k prime equal 2k, and then n squared is equal to 2k prime plus 1. So then show that n squared is odd. And that's used 4. And the definition of odd. However, if we go back to 1, we have this n squared is even in a conjunction, so we can use a simplification. So n squared is even. We can take the conjunction of these, so n squared is odd and n squared is even. So 5, 6, conjunction. This is essentially not n squared is even and n squared is even, which is equal to false. All right, so that's how we get our contradiction. So if we come to a statement that's false, then we've reached a contradiction. So then whatever we were trying to prove is not true. So therefore, what was our original claim here? N squared is even and n is odd. Is a contradiction. And therefore, what was our original? If n squared is even, then n is even. So this must be true because when we assume the opposite, we got a contradiction. Okay, any questions on that one? All right, so it is, I do like that one because you can often take something that might have been a very long, involved proof and then, and you get something that's nice and short because especially if you choose it wisely, you can get a contradiction like right away. So we assume the negation of our argument is true and show that this leads to a contradiction value of false. So this is basically just summing it up. And you can use, once you assume the negation is true, you can use a direct proof and an indirect proof or what have you. Okay, so then proof by exhaustion. So this is also known as case analysis. We have seen it already. So a biconditional proof has two cases. So this is what we use if we have a proof of implication with a disjointed antecedent. So what that means is that we have P1 or P2 or P3, et cetera, implies some conclusion. So now why does this reduce down to case analysis? Well, if we do P1 or P2, so we can use implication equivalence to get to this. Then we can apply De Morgan's on this large expression. So this becomes not P1 and not P2 and et cetera, or C, De Morgan's. So we can, since this is a a disjunction, and inside are all conjunctions. We can distribute the C among these arguments. So then we can have not P1 or C, and not P2 or C. So that's a distribution. And then we can use implication equivalence again to get P1 implies C, and P2 implies C, etc. So then, in order to prove that it's true, we have to prove all of these implications are true. So this is the case analysis. So we prove each one. We can prove each individually, the same as we did with the biconditional implication. All right. Any questions on this? You don't have to know this argument specifically, but it doesn't hurt. What you really need to know is that this is equivalent to this. If I have this disjointed antecedent, then I have to prove each of these is true. So for example, so if n is a member of the natural numbers and n is less than or equal to 3, that implies that this statement is true. And the thing about what we've defined here is that there's only 3 possibilities. So we can have n is equal to 1, or n is equal to 2, or n is equal to 3. And then our argument is that that implies that that is true. All right, so we just exhaust all the cases. So case 1. So 2 to the 3 is 8, and that's greater than, so that's equivalent to 8 is greater than or equal to 3, which is true. Case 2. So 2 plus 1 is 3 cubed. Greater than or equal to 3 squared, which is true. You can tell just by the exponent. In case 3, we have 4 cubed is greater than or equal to 3 cubed, which is also true just because the base of our exponent is greater. All right, so since this is true in all cases, and I sort of did it informally, but then we've argued our original case. We've just looked at every single case and we've proven each individually. All right, any questions? So we got a couple more to go, and then I think we will skip induction for tonight. Okay. So demonstrative or existence proof. So we want to prove that there exists an X such that P of X. So there's 2 ways to do that. We want to find a specific example and use existential generalization. So we can do that. So if we have some specific example, P of C, then we can infer there exists an X such that P of X. Right, so if we actually find an example, that's fine. There's another way, this non-constructive, we can prove something exists without identifying it. So that's a little bit trickier. So we can show there exists integers x and y greater than 1 such that x times y equals 387. And we could do that simply by finding them. So we could say, we could take 387 divided by 3, and we can figure out that that's equal to 129. So that means 3 times 129 equals 387. And then we could say, well, there exists x and y greater than 1 such that x times y equals 387. All right, so this is simply math and existential generalization of 1. So we can use an existence proof. So there is this strange fact about numbers divisible by 9. They're divisible by 9 if the sum of their digits are divisible by 9. So we could use this as our first fact. And then we could say, well, we can note that 3 plus 8 plus 7 is equal to 18. And that's just using math. So then we can say 387 is divisible by 9. And that's 1 and 2 and modus ponens, since that is, this is an implication, right? So if the sum of the digits is divisible by 9, then the number is divisible by 9, so modus ponens. And then we could say that, well, 387 is not prime. That's the definition of prime. And then, therefore, there exists x and y greater than 1, such that x times y equals 389. And again, that's just for in the definition of prime, or not prime, I guess. So we can sometimes use these math tricks to figure something out, to figure out the existence of a thing without it necessarily identifying it. So we identified x, but we didn't identify y. Okay, good. Questions? So a uniqueness proof. So we want to construct a proof that an entity is unique. So first we prove that the entity exists, and then we show that if we choose another entity that's not equal to the one that we've shown exists, then whatever we want to prove is not true. Why did we need prime numbers? Aha. Well, this is just the definition of not prime, is that there exists x and y greater than 1 such that x times y is equal to something, right? So it just means that x and y are factors of, and again, I wrote 389, it should be 387. So I use the definition of prime to show that there exists these x and y's greater than 1 such that x times y equals 387. I mean, so this is what I wanted to prove, and this happens to fit the definition of not being prime as well. So it's just a way to argue our point, knowing that we have it's divisible by one number that's greater than 1 but less than 387, which means that it's not a prime number. And if it's not a prime number, then there must be at least two factors of it that are not 1 in itself. So yeah, that's sort of, hopefully that answers your question. It's just a roundabout, I guess, clever, but in this case, maybe I should have explained it better, but clever way to come to this conclusion. Any other questions or? All right. Okay, so uniqueness, we want to prove the existence. So we want to use what we did already. And then we want to show that that element is unique. So we're going to prove this, that if we have P that's a member of the natural numbers, then there's a unique element Q such that P plus Q is equal to 0. So the existence proof is fairly straightforward. We just take Q equal to negative P, and then P plus negative P is equal to 0. So we've shown that there exists this unique element. So we found it, Q. But now we want to show that if we have some other element that's not equal to Q, then it does not fit the bill of being a unique element that we can add to P and be equal to 0. So hopefully this is, so we're arguing a little more informally here. Hopefully you're still following, but so the existence was very straightforward, and now we just want to prove that, well, if we have an R not equal to the Q that we proved up here, then this cannot possibly be true. So we're going to use a proof by contradiction using the contrapositive. Okay, so then this is the contrapositive, and we want to take the negation of that. So what we're trying to prove is this, right? This is what we're trying to prove, and this is the contrapositive of that. So then we take the negation. Actually, we can do implication equivalence first. Implication equivalence. And then this is P plus R is not equal to 0, or this is a double negation. And then to take the negation of that, well, we would take the negation of that, we can apply De Morgan's. And then we end up with, so this not P plus R not equal to 0 is equivalent to P plus R equals 0. And we could take the double negation here and say R not equal to Q. So we want to try and prove this and show that we come up with a contradiction, right? So now we're combining a few things together to do this. So yeah, 1, P plus R equals 0, and R is not equal to Q. It's our assumption. P plus R equals 0, simplification. So P plus Q equals 0, and this is existential instantiation. So this is something that we already proved. We proved there exists that. So now we can use existential instantiation on it. And then we could say P plus R. Since they're both equal to 0, then P plus R is equal to P plus Q. So 2, 3, and some math. And then we could say R equals Q. 4 and math, we just subtract P from both sides. So now we have 6. We can take the simplification. So 1 in simplification. R equals Q and R not equal to Q. So 5, 6, conjunction. And that, of course, is false, since both of those things can't be true at the same time. So therefore, we've reached a contradiction. All right, so that means we've proven that this is true. Okay. Questions? So yeah, this class is this lesson is a bit of a grind, but we're almost finished. So counterexamples. So this is our last example of proofs. Yes. Yay. Yeah, it's a bit of a grind, but it's sort of important to work through these things in detail, because a lot of these details will become important when you try and do it on your own. So yeah, I'll try and make it more interesting in the future. I'll think of something. So to prove that not for all x, p of x, it is sufficient to find a y such that not p of y is true. So we're going to find a counterexample. So I say, well, all fish live in the sea, and you say, well, no, this fish lives in a lake, so therefore what you said is false. And so what we can do is we can find an example and then use existential generalization. So using that example, I say, well, there's freshwater salmon in Lake Superior, therefore not all fish live in the ocean. So then I can use existential generalization and say, well, there exists a fish that doesn't live in the ocean. So I just want to find a counterexample. So we'll prove that it is not true that every positive integer can be expressed as the sum of two squares. So these are all the squares. So 0 times 0, 1 times 1, 2 times 2, 3 times 3, 4 times 4, 5 times 5. These are just, or, 0 squared, 1 squared, 2 squared, 3 squared, etc. So then we can look at a specific example. We could say, well, we could take 6, and we can try to add 0 and 1 together, but that's not equal to 6. We can try and add 0 and 4 together, but that's not equal to 6. And we can try and add 1 and 4 together. That's not equal to 6. And then every other number after that, starting with 9, is actually greater than 6. So therefore, 6 cannot be expressed as the sum of squares. And therefore, there exists a positive, let's say, a positive integer that cannot be expressed as the sum of squares. Okay, and that's it. So that's all of the types of proofs that we're going to look at. And actually, we're probably going to narrow in on contradiction, contrapositive, and indirect proofs. But you should be aware of these existence proofs and how to use existential generalization and instantiation and whatnot. So are there any questions on that? Okay. Scroll down a bit, please. Sure. All right, so that's it. We won't start induction today. That was a bit of a grind, and I think I would just put everyone to sleep. So we'll save that for next class, and that should fit right into our schedule. I'll stick around a bit for questions. Be sure to review the solutions for your assignment 1 and study for your quiz, and then do the quiz. And there's instructions there if you run into any technical difficulties. Please document everything you possibly can, and then email me about it, and we can arrange something. And yeah, and I'll fix the notes and these other things that I made a note of that I'm supposed to do. I'll do them. So that's it for tonight.